This is the last section of Chapter 5. We've been learning how to name compounds. We look at the formula and we write the name. And so this section is about what if you have the name and you need to write the formula. So we're going to go over these different types of compounds again, but do it in reverse. So for type 3 binary compounds. Okay, so that's the term that your book uses. I call these, I think binary compound, well, no, that doesn't even work. Binary molecular, it's not bimolecular, binary molecular. Binary molecular is a better name. These are the compounds with two nonmetals. Okay, and these are the ones that everybody likes because this is where we get to use the prefixes. And so we're starting with this one because these are the easiest ones to write formulas for. You look at the name, it tells you which two elements are there, and the numerical prefixes tell you how many of each of them. So hopefully on the next slide there's examples. No. Well, we're going to just make some examples up then. So let's say we had, of course, the creative chemistry name part of my brain is not functioning this morning. Let's say we had a name like this. Dinitrogen tetrachloride. Okay, so I am making these names up. I'm actually fairly sure that that compound doesn't exist. Doesn't matter. If we have the name, we can write the formula for it. So we look at this. Dinitrogen tetrachloride. Nitrogen and chlorine, these are two nonmetals. And so this di tells us there's two nitrogens. So we write the elemental symbol for nitrogen, and di tells us there's two. And then tetrachloride, that's chlorine. Tetra means four. So there's the formula. Let's do carbon monoxide. Well, what two elements is that? Carbon and oxygen. There's no prefix on the first one. We don't use the prefix mono on the first element. We do use it on the second element much of the time. So carbon, just carbon by itself means there's one carbon. Monoxide, mono means one, so that's one oxygen. And so the formula is CO. It's really important that your O be a capital because that's carbon monoxide, and if your O is too small, now you've got the element cobalt. And those are different. One's a gas, one's a metal. So you gotta be careful with that. Let's try, like I said, my creative part of my brain is not functioning. My sense of humor is a little on the wimpy side today too, which is very, very bad. Sulfur hexafluoride. What would the formula for that one be? SF6. SF6. So sulfur, there's no prefix, so it's just one. Hexa is a prefix for 6. A hexagon has 6 sides. Another way you can remember that is hexa and 6 both have an X in them. None of the other numbers or prefixes have X's. So, any questions about writing formulas for these guys? Usually people don't have much trouble. The hardest thing about these is remembering some of the odd prefixes. Tetra meaning 4, hepta is weird. Hepta means 7. And then, of course, you need to know your element names and symbols. So, ionic compounds. When we're writing formulas for ionic compounds, we first need to write the formulas for each ion, including the charges. So you need to do a little work on the side before you write down the formula. The charges are important because that tells us how many ions of each are present in the formula. Then we write the formula. We're going to use parentheses if we have multiple polyatomic ions. Remember, polyatomic means many atoms. So this is an ion that has more than one kind of element in it. When you have more than one of those, then you need parentheses. The polyatomic ions are like a bundle pack, that something you buy at Costco, and you get multiple things bundled together. And the parentheses are like the shrink wrap, and then the number on the outside tells you how many packages you have. In the formula, do not show any charges. So use parentheses for polyatomic ions if we have more than one, and don't show any charges. Yeah, there's no examples there either, so we'll make some up. How about we go into the drawing mode first? That would be helpful. Let's do tin 4 oxide. This is an ionic compound. How would you identify that? Well, one way is anytime you see a Roman numeral, it's going to be ionic. The other thing is find this first element, tin, on the periodic table and ask yourself, is it a metal? If the first element is a metal, it's ionic. So what we need to do is we need to write the formulas for these ions. There's always 2 ions. And there's 2 words. So we've got tin 4 and we've got oxide. The element symbol for tin is Sn. And the Roman numeral 4 tells us that the charge is 4+. Oxide is the ion of oxygen. The symbol is O. We find the charge of oxide on the periodic table. It's in group 6, or we count back from the far right, from the noble gases. This is 0, -1, -2. So oxide has a -2 charge. And this stuff here, this is really, really important to be able to do. You have to write the formulas with their charges. Now that we have these 2 formulas, we've learned how to put these together. So we'll go with the more straightforward way of just kind of drawing pictures and thinking about it. So we need the total of the negative charges on the right to equal the positive charges on the left. Over here we've got +4, and here we have -2. Those are not equal. We need more negative charges. So let's add another one. That's all we can do. You can't add something with a different charge. You can't add something else. All you can do is add more of the same. Well, if we've got 2 of those, now we've got a -4 charge. So this tells us that we've got 2 of these guys. So then in the formula, it's going to be SnO2. 1 tin ion and 2 oxide ions. We don't need parentheses because this is a monatomic ion. It's just oxygen. It's not phosphate or sulfate or something like that. Any questions about this one? So let's make up some more. How about sodium nitrite. Well, we need to identify what kind of a compound it is, and that first element often tells us sodium is a metal. So this is ionic. Ionic compound, we first write the formulas for both of the ions. There are two ions, sodium and nitrite. So sodium has the element symbol Na. There's no Roman numeral given. That means we can find the charge on the periodic table. Sodium's in group 1, so it has a +1 charge. Nitrite. Okay, that kind of looks like nitrogen, but if it was just nitrogen, it would be nitride. This is one of those polyatomic ions. And so you go look in the table. I have the table in my head, so I'll look it up for you. NO2 minus. We've got the formulas for each ion with their charges. Really, really important. Because the charges tell us how many of each. We look at these charges here, we've got +1 and -1. So we don't need to do anything fancy or add any more. If we just push them together, +1 and -1 add up to 0. So we just push them together, and the formula is NaNO2. This is a polyatomic ion, but there's only one, and so we don't need parentheses. Let's do another one. Let's do calcium chlorite. Chlorate. We'll do chlorate. I don't know why. Calcium chlorate. Most compounds have two names, two words in their name. So this calcium chlorate, first we'll look up calcium in the periodic table, and we see that it's a metal. Remember, metals are elements that are to the left of the stair-step line. This is a metal, so this is an ionic compound. We write formulas for each of the ions. What's the element symbol for calcium? Ca. And what group is calcium in? It's in group 2. So the charge is 2. If there's no Roman numeral, we get the charge from the periodic table. If there's a Roman numeral, then we just write that down as the charge. Chlorate is a polyatomic ion. So you look that up in the table as ClO3, and the charge is -1. So we look at these charges. We've got +2, we've got -1. Those don't add up to 0. We need another chlorate, don't we? If we had 2 chlorates, now we've got a total of -2 over here and +2 over here. Does that make sense? Because if it doesn't make sense, then you're never going to be able to remember how to do it. So in order for the charges to balance, we need 2 chlorates and 1 calcium. So then in our formula, we write calcium. Now we've got 2 polyatomic ions. If we just do ClO3 and put a 2 over here, that looks like we've got 32 oxygens and 1 chlorine. And that's not what we meant. This is one of those bundle packs. We've got ClO3, and we put parentheses around it to show that we have 2 of those units, so that it's less confusing to someone looking at it. Does that make sense? So that's calcium chlorate. How about iron 3 sulfide? Well, the Roman numeral here tips us off immediately. This is an ionic compound. Iron 3. So we need to know the element symbol for iron, which is Fe. Iron is in the middle It's one of those transition elements. We can't tell its charge from the periodic table because it actually forms two differently charged ions. But the Roman numeral tells us. The Roman numeral is the charge. It is not how many. Sometimes students will want to put Fe3S. Okay, and then no, you're mixing up the prefix thing with the Roman numerals. This is the charge. This is 3 plus. That's easy, right? It tells you what the charge is. Sulfide is from sulfur. Now, if you look at these guys up here, this ended in TE and this ended in TE. Many of the ones that are polyatomic end in TE. This ends in "ide." Most of the ones that end in "ide" are just a single element. So this is sulfur as an ion. Just like when a woman gets married, she often changes her last name. The nonmetals are feminine in my crazy chemistry world. I need to come up with a name for my chemistry world. Anyway, those are nonmetals, so they change their names when they hook up in a compound. So sulfur becomes sulfide. And what's the charge on sulfide? Just count backwards. 0, -1, -2. This is a -2 charge. 2 minus. Then we look at the charges. Are they the same? No. One's 3 and one's 2. That's not going to add up to 0. I probably didn't leave enough space here. This one, when we do it, the just drawing in more ions thing kind of gets ugly for a while. So we look at this, and here we've got +3, and here we've got -2. So we're short on the negative side. So we need to put in another sulfide ion, and that'll give us -4. Well, now we're short on the iron side, on the plus side. So all we can do is add another one of these. And that gives us +6. I'm like, good grief. Well, now we're short on the negatives, so we'll add another one over here. And then we say, oh, thank goodness, it finally balanced out and came out even. So that's one way to do it. And we look at that and we see we've got 2 irons and 3 sulfurs, and so that would be Fe3S2. Another way to do it is to look at those 2 ions, and we see the charges are not the same, so we can use the crisscross method, and that becomes the subscript on the sulfur, and this becomes the subscript. Okay, stop me when I do that. I screwed this up. That's wrong. Yeah. Yeah, it's one of those days. Because I can't count today. There's 2 irons and 3 sulfurs. The crisscross method, this charge becomes the subscript here. And the charge on this one becomes the subscript over there. That works probably 95% of the time. Not foolproof, but 90% is pretty good. So that's the formula for iron 3 sulfide. This whole business over here reminds me of my Grandma Johnson. She liked to eat. And, you know, we'd have bread and like jam or something with dinner. She called it bread and with it, because with it could be anything. It could be butter, grape jelly, strawberry jam, whatever. And so she'd take some bread and she'd take some with it, and then she'd put the with it on her bread, and then there's jelly left over, right? So we can't waste the jelly, so she'd take another roll and she'd start to put the jelly on the roll, but there wasn't quite enough jelly, so she'd have to, and she could go on eating bread and with it for a really long time. And sometimes when you're looking at trying to get these to balance out, it feels like it's never going to work out, but it will. If you like math, what you're really looking for here is the least common multiple. Okay, the smallest number that has 3 and 2 as a factor. So some of you will go, oh, and others of you will go, what? So if you're saying what, then just ignore that part. Any questions about this process for ionic compounds? No? Okay. Acids. Writing formulas for acids. Remember, we had two kinds of acids. And when we look at their names, acids are really easy to recognize from their names because they all end with the word acid. It's really nice that way. To distinguish between the two kinds of acid, look at the beginning of the acid name. Acid names that start with the word hydro or the prefix hydro do not contain oxygen. We call them binary acids, and they contain two elements except for hydrocyanic acid. So these are just hydrogen, a hydrogen ion with an anion. And so we're going to figure out how many hydrogen ions we need based on the charge of the anion, and we'll do a couple of examples. Oxyacids, this is where we have us and ic in the name, like sulfurous acid or sulfuric acid. It does not start with hydro. And so then you have to look at the name and figure out what the anion is. And the only way we can make any sense of this is to do some examples. So let's do hydrosulfuric acid. Recognizing that as an acid is easy. It says acid in it, right? Isn't that nice? This prefix hydro tells us that what we've got here is we've got a hydrogen ion, and then we've got a sulfur ion. Sulfuric, hydrosulfuric means hydrogen and sulfur. So we've got hydrogen and we've got sulfur, and then we need to figure out what the charge on a sulfur ion is. So we look at the periodic table. 0, -1, -2. So this is S2-. And so we're going to treat them like ionic compounds and use the charges to put the right number of hydrogen ions together. So how many hydrogen ions does this one need? 2. So the formula is H2S. That's hydrosulfuric acid. What if we had sulfuric acid? Those two names are pretty similar, aren't they? One has the prefix hydro and the other doesn't. It matters. Sulfuric acid has an oxyanion. It's got hydrogen and sulfur with oxygen. And to find out what that ion is, we look at this suffix, ic or ate. This is where we had that sentence, Rick ate him before he could bite us. Ic and ate go together. So sulfuric tells us that this has the sulfate ion in it. So then we have to go to the table and look up what the sulfate ion is. We look it up and it's SO4 2-. And acids always have hydrogen. And so then we look at this and we have to decide how many hydrogens. Well, because hydrogen is +1, whatever this charge is the number of hydrogen ions you're going to need. So this is going to be H2SO4. It's a bad 4. That's a little better. Hydrosulfuric acid, sulfuric acid. H2S, H2SO4. Little differences, but they're important. Let's do one more. This is one of my favorites. It looks like periodic acid, right? Like the periodic table. It's not periodic, it's periotic. So you look at that and you're like, what on earth is that? Well, it doesn't have hydro. And thankfully I'm not giving you oral exams or anything, so you don't have to actually pronounce these things to me. It doesn't have hydros, so this comes from an oxyanion. So ic, we change to 8. So this has the per iodate ion in it. And then you go to the table to look that up, and you can't find it in the table. You go, what is she doing to us? Well, periodic table, chlorine, bromine, and iodine are sisters in the halogen family. And now, among my children, I only have one daughter, but I have 5 sons. So there's 5 brothers. Are they exactly identical to each other? No. But they do a lot of the same things because they're brothers. They all like football. Andrew's only 5, so he's not able to play tackle football yet, but he would if he could. Chlorine, bromine, iodine are sisters. They're going to form ions in the same pattern. So can we find one of iodine's sisters in the table of polyatomic ions? We can. Chlorate is in there. So there's chlorate and there's perchlorate. So perchlorate is the name that is like periodate. We're just swapping sisters here. So perchlorate is ClO4 minus. And so to make periodate, we're just going to swap in an I for chlorine, and we're going to get IO4 minus. You can do this with bromate too, bromine. And so there's our ion, IO4 minus, and we need an H plus. This is a -1 charge, so we're just going to have one of each. And periodic acid is HiO4. Any questions? We're going to do some more examples. I know there's example slides at the end of this. Here's examples. So these are all mixed up. So we've got sodium hydroxide, potassium carbonate, sulfuric acid, dinitrogen pentoxide, and cobalt-3 nitrate. And we need to write formulas for these. So let's start with the first one. Sodium hydroxide. Well, what kind of a compound is it? What kind of an element is sodium? Is it a metal? It is. So this is ionic. That means that we have to write the formulas for the ions. So what's the formula for sodium ion? Na, and what charge does it have? It comes from the group number, +1. Hydroxide. It kind of sounds like hydrogen, kind of sounds like oxygen, but it's not either one of them. Maybe it's a polyatomic ion. So go look on the table. We look on the table and we find that hydroxide is listed there as OH minus. Then we look at the charges. We've got +1 and -1. They're the same but opposite, so all we have to do is shove them together. And we've got NaOH. Notice, in the formula, we don't write the charges. Things would get very cluttered if we wrote all the charges in there. So we don't write the charges. Potassium carbonate. Well, again, potassium is the first element. What kind of an element is it? Metal or nonmetal? It's a metal. So we've got an ionic compound again. So potassium is K, and what's its charge? +1, because it's in group 1 in the periodic table. All the group 1 elements form +1 ions. Carbonate. Okay, we've got this Te. That gives us a clue. This is probably a polyatomic ion. Let's see if we can find it in the table. So as you can imagine, you're probably going to want to have a copy of that table of polyatomic ions handy so that you can look at it. And I will give you one for the exam. So carbonate, you look in there and you find CO3, and it has a 2- charge. The charges tell us how many of each. This is +1, this is -2. Those are not the same. So we can think it out, or we can do the crisscross thing. If we do the crisscross thing, this is an understood 1. That becomes the subscript on the carbonate, which we don't write there either. And this is a 2, which will become the subscript on the potassium. So this has the formula K2CO3. Any questions? What kind of a compound is sulfuric acid? Maybe an acid? We just did sulfuric acid, so I'm going to change this one. Let's make it phosphoric acid. So phosphoric acid. We had 2 kinds of acids. The ones that were just basically 2 elements, and the ones that had oxygen in them. Which one is this? This is the one with oxygen. The ones with 2 elements start out with hydro. So if it was hydrophosphoric acid, then it would just be hydrogen and phosphorus. But this is phosphoric acid, and so this is where we change this ending. I'm sorry, all my examples have been the ick ones. It's because it's an icky day. So that comes from phosphate. These endings go together, ick and ate. Phosphate is the ion. And so then we have to find the formula for that. Well, it's PO4 3-. And then with an acid, the cation is always H+. So for acids, it's easier. We just look at this charge. It's 3, and that tells us pretty much automatically it's 3 hydrogens. H3PO4 is phosphoric acid. Dinitrogen pentoxide. Well, what do we see about this one that's different? Prefixes. Those lovely numerical prefixes. So these are easier. Here, this is telling us there's nitrogen, and di means 2, and here is oxygen, and penta means 5. So dinitrogen is N2 and 5 oxygens, O5, N2O5. I don't do as many examples of those because students usually catch on to that pretty quickly. It's the acids and the ionic compounds that are tricky. Okay, this last one, cobalt-3 nitrate. The Roman numeral tells us right away ionic compound, because only ionic compounds use Roman numerals. So cobalt is one of those elements we don't use quite as much, but cobalt is CO, and that second letter is lowercase. This 3 tells us that it's 3+. So if we find it on the periodic table, it's right there in the middle, the transition elements, and we can't predict their charges. So CO 3+, and then nitrate, again ending with the TE, this is a polyatomic ion. So we look it up, NO3-. You have to write the ions with their charges. You really just have to. Then we can do the crisscross thing, because 3 plus and -1 aren't the same. So this is going to become the subscript for the nitrate. And this 1 that we didn't write is going to be a 1 that we don't write as a subscript on the cobalt. So CO And we've got 3 nitrates. That's a polyatomic ion. We need to put shrink wrap on it and put this 3 on the outside. Any questions? I don't know what that was about. The computer's complaining to me. Let's do a few more examples. What? Okay, let's do a few more examples. Let's do blue for a change. Let's see. Let's do hydrobromic acid. So hydrobromic acid. What would the formula for that be? So we have a guess of HBr2. Just one, there we go. Okay, so why is it 1? Well, hydrobromic, this prefix tells us this is a binary acid. There's no oxygen involved. So bromine means there's bromide ion involved. We find the charge of it, it's -1. And all acids have H+. Here we got +1, -1, we just shove them together. And the formula is HBr. How about nitrous acid? No hydro in front. So this is where we have to look for the polyatomic ion. So nitrous, the us comes from ite. So this is from the nitrite ion. So we look that up and it's NO2 minus. And then we have to put that together with hydrogen ion because that's what acids are. Again, we've got +1, -1, so we can just put them together, HNO2. That's nitrous acid. Nitrous acid and nitric acid are not the same. They're different. Let's do another one. How about silver oxide? Silver oxide. Well, what kind of an element is silver? It's a metal, right? So this is ionic. So we need ion formulas. So we've got Ag. What's the charge on the silver ion? +1. How do we know that? Okay, this is one of those, it's a little trickier. We look at the periodic table. Aluminum is in group 3, aluminum's +3. And then we go down the stairs. Zinc is down 1, that's +2. Silver is down 1 more, it's +1. Zinc and silver are the two that you just have to remember. So silver is +1, and oxide is what charge? 2 minus. So then we need Ag2O. So you could do the crisscross thing, or you could look at this and say, oh, well, I need another one of those so that I've got +2 over here to balance the -2 over there. There's many different ways of thinking about how you put those ions together. So if one of the ways that I've given you in class hasn't clicked with you yet, please ask me either by email or text message or during class or after class or something, because I've got a whole bunch of other ways. And I can make it click for you. And once it clicks, it's just so much easier. Any questions? Well, we are close enough to out of time. So enjoy your 4-day weekend. We're going to do a worksheet on nomenclature in class on Wednesday. So it will be very helpful if you go home and work on this stuff. You've got a whole week, okay, to either learn it or forget it.